Welcome. Today, we move beyond the cultural ritual of Kakie and enter the laboratory of close-range physics, analyzing the sticky bridge as a mechanical coupling. We dissect the forces at play in the tactile bridge. Kakie involves tactile sensitivity, Muchimi or stickiness, and kuzushi, which is unbalancing the opponent. This requires understanding the internal forces and external force vectors. The term Kakie has roots in Fujian dialect, tracing its origins from Lakchuguan, meaning power, hand, and source, adapting into the Okinawan and Japanese phonetic form. The Sino-Ryukyuan lineage of this practice connects Fuzhou in China to Naha in Okinawa, reflecting the historical transmission symbolized here by the white crane connection. The core philosophy is Go and Ju, hardness and softness. Go relates to force and mass, represented by a solid rock. Ju relates to torque, or rotational force, like the movement of water. We bridge because vision is too slow. Visual reactions take about 200 milliseconds. Tactile reflexes, however, bypass the visual cortex, allowing instantaneous subcognitive reaction in 30 to 50 milliseconds. Sticking is governed by tribology, the science of friction and adhesion. The limit of this stickiness, or maximum static friction, is simply the coefficient of friction multiplied by the normal force N. Therefore, to control the stick-slip phenomenon, we must actively modulate the pressure, N. Force is borrowed from the earth. The body acts as a tensegrity structure. We use the ground reaction force, transmitted through the latissimus gluteal sling, to drive force into the bridge. Muscles are viscoelastic, behaving like a fluid and a solid. Muchimi, or heavy hands, exploits strain rate sensitivity. Moving slowly prevents the opponent's tissues from stiffening, bypassing the stretch reflex. Mastery involves dynamic impedance control. High impedance is stiffness, for blocking or striking. Low impedance is damping for absorption and flow. We rapidly tune these parameters to match the opponent's energy. To unbalance the opponent, we must generate torque, tau. We achieve this by maximizing the moment arm, the distance, r. By applying a force couple, simultaneously pushing and pulling, we force a rotation specifically around their center of mass. The whip effect utilizes the conservation of angular momentum. By spiraling the bridge inward, we decrease the radius, which decreases the moment of inertia. This increases the angular velocity, whipping the opponent off balance. True damage is the transfer of momentum, governed by the law of impulse, symbol J. Mathematically, this is force, multiplied by time. The heavy Kakie strike engages effective mass and deliberately lengthens the contact duration. This maximizes the total momentum transfer, sending the energy deep through the target. Joint locks exploit mechanical advantage. An attacker uses a highly efficient lever structure against the defender's less efficient Class 3 lever, generating torque that exceeds the joint's elastic limit. In the full-flirting throw, the hip acts as a fulcrum below the opponent's center of mass. We displace their center of mass outside their base of support, converting potential energy to kinetic energy via the drop. Kakie is applied physics. It relies on haptic speed, friction management, structural tensegrity, and mechanical advantage. We train to become tactile physicists, solving mechanical problems in real time. Thanks for digging into the past with us today. If you enjoyed this analysis, help us keep the expedition going by hitting like and subscribe. For more lost history and strategic breakdowns, click the video on your screen now. Train hard, study history.